Hey everyone, and welcome. So, we're about to dive into one of the most incredible, most counterintuitive ideas in all physics. What if I told you that our basic idea of empty space, nothing, is completely, fundamentally wrong? Let's just jump right in with a question that sounds so simple, but it's one that has kept physicists and philosophers up at night for centuries. What is nothing? I mean, really, when you imagine a perfect vacuum, what do you even see in your mind's eye? For a long time, the answer was pretty simple. It was the classical view. Nothing is just, well, nothing, an empty, boring void. But then quantum mechanics came along and flipped the whole idea on its head. The quantum view says that the vacuum is anything but empty. It's a seething, bubbling, chaotic sea of activity. So how is this even possible? How can nothing be so jam-packed with something? To really get this, we need to meet the bizarre, temporary residents of this so-called empty space. And here they are, the main characters of our story, virtual particles. You see, thanks to the wonderful weirdness of quantum mechanics, pairs of particles, like an electron and its opposite, a positron, can literally borrow a tiny bit of energy from the vacuum to pop into existence, just for a fraction of a second, before they slam back into each other and disappear. Now, you might be thinking, okay, a sea of particles popping in and out of existence, so what? Well, it's not just a weird quirk. This chaos actively changes how the universe works through something called vacuum polarization. Basically, when you stick an electric charge, like an electron, into this quantum vacuum, the vacuum doesn't just sit there. It responds. The electric field from that charge actually organizes the chaos of virtual particles around it, and the vacuum itself starts acting like a physical substance. So get this. Picture our electron sitting there. All these virtual particle pairs are popping into existence around it. But the virtual positrons, the positive ones, get pulled a little closer to our electron, and the virtual electrons, the negative ones, get pushed a little farther away. This creates a tiny halo of positive charge right around our original electron, acting like a shield. It means the charge we actually measure from far away isn't the electron's true bare charge. It's a weakened, screened version of it. Okay, I know what you're thinking. This sounds like some wild science fiction, right? A quantum shield made of nothing? But here's the kicker. This screening effect has real, measurable consequences that we have tested with mind-blowing accuracy. Let's rewind to 1947. Physics had a major problem on its hands. Our best theory at the time predicted that two specific energy levels in a simple hydrogen atom should be exactly the same. But when a physicist named Willis Lamb measured them in the lab, they weren't. There was this tiny but undeniable difference. Our theories just didn't match reality. And the solution? You guessed it, vacuum polarization. It turns out that an electron in one of those states spends just a little more time closer to the nucleus, punching through that virtual particle shield. By doing that, it feels a slightly stronger, less screened pull from the nucleus, which gives it a tiny bit more energy. And that tiny energy difference perfectly explained what Lamb had measured. It was the missing piece of the puzzle. But physicists wanted even more proof. They wanted a slam dunk. So they turned to the electron's heavier cousin, the muon. This thing is a beast. It's over 200 times more massive than an electron. Now, because it's so heavy, a muon orbits incredibly close to the nucleus. We're talking deep inside that virtual particle cloud. This means the screening effect is way, way stronger. And when physicists did the experiments, the energy shifts they measured in these muonic atoms matched their predictions from vacuum polarization perfectly. It was a total game changer. But this concept did way more than just explain a few strange measurements. Taking the quantum vacuum seriously was absolutely critical to fixing some of the biggest, ugliest problems in all of physics. You see, without this idea of vacuum screening, our equations were literally breaking. They were spitting out absurd, infinite answers for simple things like the mass of an electron. Vacuum polarization was a key part of a new technique called renormalization that allowed physicists to tame those infinities and get real answers. The result was a theory called quantum electrodynamics, or QED, which is, to this day, the most accurate and precisely tested theory in the entire history of science, period. So, let's just take a step back and think about what this really means for our entire picture of the universe. This quote just nails it.
The vacuum isn't just an empty stage where reality happens. It's an active player in the game. It's a dynamic, powerful medium that actually helps write the rules of physics as we know them.
It's a truly humbling thought, isn't it? The empty space right here in the room with you is actually a seething, frothing ocean of potential. And it just makes you wonder, if we were so fundamentally wrong about nothing for so long, what other giant secrets about the universe are hiding in plain sight?